This conference will now be recorded.
All right, good morning. My name is Greg Wadley with CTC & Associates, and I'm the Clear Roads Administrator. We're here for the final webinar for the project entitled High Performance Blade Evaluation. This research effort is led by Bill Schneider at the University of Akron. Before I turn it over to Bill, I want to let everyone know that this webinar is being recorded and will be posted on the Clear Roads website at a later date for viewing at your convenience and for your colleagues. We'll also ask that everyone stay off camera and stay on mute so that there's no background noise and we have appropriate bandwidth. However, if you have any comments or questions, please enter them into the chat box and we'll address them at the end of the presentation. I think that's it for housekeeping items, so I'm going to turn it over to you, Bill.
Okay, Greg, thank you for the intro. I'd like to thank everybody for taking some time out on their Friday morning to go over a little bit with this project. This first slide here is our title. You can see we had two universities associated with this work, and then later on in the presentation, you'll see that we had a outside lab that was doing some contract work with some of the blades that we were studying along the way. I'd like to reach out and shout out to our technical panel, who you can see here, and I'd also especially like to thank Greg for his help on this project. This was our first project with Clear Roads, and I was talking with Lindsay earlier this morning, and this project started in basically the summer of 2019 is when this project started. So we did pre-COVID, COVID, and then hopefully post-COVID on this presentation. So again, I'd like to thank Greg and the rest of the team here for staying with it through this whole process. So what we're going to do today is we're going to go over some of the work that we did on the project. Given that it was several years, there's a lot of work that we did along the way. Ultimately, the main goal was to take a look at how snowplow blades wear, and is there something that we can do from a Clear Road standpoint or from a DOT standpoint that will make things better for both the state and the public. So when we look at blade wear here, it's sort of a flow chart that kind of brings everything together. On the wear, you've got normal conditions, and then you've got abnormal use. So the argument is if it's under normal, you've got you're looking at the bottom left here, the blade material, the longevity of it. What kind of road are you driving on? How bad was the weather that season? Did we get a lot of snow? Did we get no snow? Was a lot of ice? What was it there? And the argument is that blades over time are going to wear out. So if it's under normal conditions, can we come up with some sort of factor there? Now, on the other side is abnormal use, and I think any DOT that's been or any DOT professional that's been working in this field for a long time knows that we have blades that break for a wide range of uses or reasons. On the blade use side there, is it something wrong from a manufacturing standpoint? There's something that isn't quite right with the blade. Or the misuse side, is it an operator error? Is it using the wrong blade for the wrong conditions? So, this is sort of the 20,000-foot view of blade wear that we're talking about. Now, in terms of deliverables, this project was about, started in summer of 2019. We've had multiple extensions on the project. We've had one large-scale addition, which was lab testing, which wasn't in the original document or scope of work, but throughout the time and the process that's evolved, and we've included that in here. So in general here, we had 9 different tasks associated with this project. We had the standards, the literature research, the state of the practice. We looked at some blades for field testing. We did some field testing designs. We looked at, developing some standard protocols, some cost benefits, some lab testing, all in there. And that's where we are. What I also did to help with this presentation is as I've added the figures that are in our final report. So later on, if there's a question here, there'll be a way to refer it back to the final report to get some additional answers along the way. So the first phase of this project was we were to do large-scale field testing. And so basically, when you're looking at the grand scheme of how this project went down, we did large-scale testing, we did small-scale testing, then we did some lab testing, and then ultimately from there, we were trying to figure out what's the best approach, if you will, coming through it. So I added some of these flow charts in here, again, 10,000, 20,000 foot views to help everybody out. So on the large scale testing, this is basically looking at, can we use GPS, ADL, or can we use some other form and test, you put the blade on the truck, you drive the truck around for a season or two, and then you measure the wear of that. And can we kind of link the wear with the pavement conditions, with the weather and all that stuff? So we broke this down into basically from a method of collection point of view, you have GPS, you have the ArcGIS roads layer, you've got weather data, and then coming from that, what data could you collect from it? So, GPS, depending on your system, it could be everything from plow up, plow down, to speeds, to where were you at. ArcGIS, what roads are you working on? Weather data, obviously it's weather data. And then at the local level, so you've got sort of a state level big picture, and then you've got a local level there, which is the blade specific, you've got the mechanic, and then you've got the operators there. And then from there, you look at, what data were you collecting on the blade? The angles, the wear, the installation, was that all done properly? How did the operator feel about that blade, if there was an opinion? So that's much more at a local level. You'll sort of look at the top tier as state level, local level as really the garage or a district or a county, however a state DOT would look at that data. In this case here, we, that winter there, again, remember that winter would have been winter of 20. So it was right before, right at the beginning of COVID. And so we got, Idaho agreed to work with us on collecting some data. They had some the equipment necessary, and more importantly, they had the resources to help out with collecting of some data. So what you see on the left-hand side of this is our table of how we were collecting that data in conjunction with Idaho. And so, whether it's the GPS per storm, the ArcGIS layer, once a time, the blades, however that was split out. And then the right-hand side of this presentation here, we have the two counties that agreed to do some work with us over the winter of 20. From that, we were able to collect some data. And again, I'm not, due to the time limits of this presentation and the scope of all the work that we're doing, we're just highlighting some of the things that came across. But again, in each of these cases, I'd refer you all to the final report because that's going to give you some additional information there. So what we basically did in this study is we looked at everybody. We had them measure 5 different locations after multiple storms and see how their wear was at. And then we looked at, their distance plowed and some of the costs associated with it. So the left shows how the wear evolved over time. the right shows a sample table of information that we collected at the time, at the time. So we did that at a large scale, and then at the same time we were doing that, we were working with some colleagues out in Norway, and what they did is they looked at it at a small scale. So we looked at sort of the pluses and minuses associated with both kinds of studies. So in the large scale, you're talking district or county level, maybe state level, and you're not necessarily you're using the existing system as a supplement to your data. Meaning, again, they're already calculating this stuff. Then can we use this data to find our findings? And then in the small scale study here, what we were able to do is you're able to control a lot more. So you're not just looking at, various pavement types. You can really hone in on one spot. And in this case here, our colleagues in Norway were actually driving in some cases with the operators there and doing a lot more hand counts. Pro, this is you can control the situation a lot better. The con is it's a lot more expensive to collect the data because, again, you're looking at one truck versus a fleet of trucks, if you will. So on this one here, left-hand side shows the routes that we're using. Right-hand shows the type of vehicle that their plows are using. So it's just an interesting study that they did. What they did there is they measured in 6 places there, as you can see. On the left-hand side shows their protocol. And then again, similar to our side, we did 5, they did 6. And then on the other side, the right-hand side, you can see how the wear increased with distance there. So again, not surprising that's how the data shook out. The longer you're driving, the more wear you have. Now, what's interesting there is when you look on the right-hand side, they were really testing 2 different blades there. And you can see how those distances versus wear were impacted as you go through your study. So then what we tried to do in both cases is, I think, similar in approach to what a lot of people do with buying cars or buying other equipment. The initial capital cost versus the cost to keep it going versus cost to keep it going versus how long do you want to have something. And what I kind of think about that is on a bigger scale. Again, do you buy something that's cheap knowing full well that your plan is to throw it out relatively quickly? Or do you buy something that's more expensive and try to keep it for a longer period of time? And so what we have here is on the left, we have a discussion of what we were looking at is cost neutrality. And what that is it's basically saying that if I have one blade, and let's hypothetically say that it's $1,000, and that includes all components with that. So whether it's the installation, it's the purchase price, it's everything associated with $1,000. And then you look at another blade and you say that total cost is $3,000. So for things to be cost neutral, the example would say that the $3,000 blade needs to go for 3 times the length of time as the $1,000 blade. And again, the assumption that we're making here is that all costs are associated with it. And what you can see here when we're looking at our cost neutrality, we highlight a few different equations in our book that talk about those specifics there with the cost. And then what we can see here on the right in figure 19, we did this a few times. This one is based on a standard carbon insert. The x-axis is the cost difference between a new blade and an old. So what they're saying is in this case here, my new blade is something I'm going to try versus an old blade that we know works. And you'd say, okay, then the y-axis is the wear rate in inches per mile. So negative means that it's actually performing better than what we saw. And there, you can also see in there are two distinct lines which represent the cost neutral blades in there. So those are those two dotted lines. And we did this using a few different data sets. We used some of the data that we got from Idaho. There's a former Clear Road study. I think it was done in, and I apologize, I don't remember the number. I think it was done in 2013. And then we did a study back in the day for ODOT. So we incorporated a bunch of that data in there to kind of generate some areas of interest, if you will. And what you're seeing is that the expected wear and the cost of the dotted and dashed lines. And when the cost is less than expected, it's in the upper right of the graph, which is when the cost is negative and the rate wear is positive. So what that's saying is that your new blade with the cost and all that stuff is actually more expensive over the long haul than some other blades. The bottom example there is where it's good. So in those situations there, you're saying, well, yeah, the cost of the new blade may be more expensive, it may be less expensive, but it's performing in a way that suggests that it's something to consider. And what you can see there too is we have a few different dots on there that show some of the examples of the blades that we used on a large scale. And that is where some of those blades would fit in. So are they cost neutral? Are they bad, more expensive? Or are they better in the long term? And one of the things that we were trying to do is whether it was the large scale study that we did with Idaho, the small scale study that we did in Norway, or future studies that an individual DOT might consider doing, is coming up with a methodology that a DOT could then potentially use to evaluate cost neutrality. Because the ultimate goal is to save taxpayer money and to provide the traveling public with better performance on the roads. So this is a protocol that we were looking at. Now, with that, about I'm going to call this December of 2020-ish is when we started talking about at our meetings that it was hard to get a lot of good data with respect to our findings with the large scale and the small scale, and there's a lot of reasons for that. So one of the ideas that was floated at that time was to see if we could look at a laboratory setting to see, is it possible for us to cut a blade open or scan it or do some other things associated with it. So the picture here that we're showing is the standard Polar Flex blade, and it was ultimately the Polar Flex blade that we decided to look at in the next phase of the study. And it makes sense because it's a complicated blade in some aspects, because it's got a braze point to it, it's got a carbon insert, it's got rubber, it's got steel, it's got a lot of stuff associated with it. And then the Polar Flex is a very commonly used blade in the field. So on both sides, it made sense to look at this blade in more depth. So the first thing that we did is we did another review of what's standard practice. We called a lot of the blade manufacturers, and we just hopped online and we looked at, okay, what labs are there out there? Because at the end of the day, this is a research project. So there was no standard, this is how you test the blade. And even when we talked to manufacturers about it, a lot of manufacturers did not have consistent, this is how everybody should test blades. And there's probably a wide range of theories as to why that's the case. So the first thing we did is we went out and we tried to find as many labs in this country that would help us out. And we basically reached out to 20 different labs. You can see the statistics here. And we just said, hey, you know, you guys are more in the business of this than we are. Can you help us out in terms of coming up with some tests that we could look at? And we had a wide range of answers there. Many of them said that they could. So then what we did is we said, we came back to our panel. We said, we've got a company here, and this is what you're seeing here on our slides. Element Materials Technology. They were part of the original testing that we did. And then what we did is we asked a bunch of a bunch of labs if they would be interested in doing the testing for us. And so we had to do some discussions between Akron and the labs to figure out which tests to do and how the cost and all that stuff. And ultimately, this company here seems to be, it's who we selected, and I very much appreciate their work. This part of the study is seen in chapter 4.6 of our final report, and similar to the large scale and the small scale testing that we've already done, I've just put some of the highlights in there. So just some examples of how some of the tests would be run. There are a lot of tables in that report, in that section, that has very specifics in terms of composition of various items that are within those blades. But again, I'd like to thank Element for their help. Dustin did their metallurgical work and testing, and Elena did their polymer work. So we kind of broke it down, metals versus polymers, to see what we could do. Now, what we've started looking at, and one of the goals that we're trying to do is we took random, the ASTM standards that we found from interviewing the 17 various labs, and we said, hey, does that make sense? And what could we potentially find? What would that number be? If that number is high, would that suggest that blade wear would be better or worse, and some things like that? So we have some basic tests and descriptions on the lab. So everything from chemical analysis to carbon density to cross sections to scanning electric microporosity and EDS, which is energy dispersive spectrometer in there. We did micro hardness, and we did Fourier transform infrared spectroscopy. So I encourage you again to look at it, and then we did sort of this low results. Like, what would you expect to see? You know, and so like the carbon density, how dense is the carbide? You know, and then we looked at it there in terms of just the general low, medium, and high. And we'll break those prices down for you in a few slides down the line. And then we looked at this sort of like a priority, like what do we think would be better or worse? And again, in a few slides from now, we'll break down both the metal side and the polymer side into this. So again, the goal is just to sort of help people out moving forward. Again, some more examples here of some other tests that we were looking at in terms of moving forward. So what we did is we basically, this is what we did. We went back to our panel. We were able to get some samples of new and used blades. You can see 3 examples on the left. 2 of those are from North Dakota. Top one's North Dakota. The middle one in figure 418 is a used blade from North Dakota, and the bottom blade there is an example from Iowa. So we used a few different sets of blades there. and we were really in the grand scheme of things, since this is the first time it's been done, we were looking at, let's try a few different kinds of tests, flat out, not, we had an idea of what it would show, but not 100% what it would show. So we looked at that. And then on the right-hand side there, figure 419, there's three different spots that, that we were looking at. One is you can see a green arrow with a ring at the top. You see a blue arrow down at the bottom, and then you see two lines. There's a yellow line at the top middle, and then there's an orange dash line. They're running parallel to the blade edge down near the bottom of that blade. And so what we did is we went back to the labs and we said, hey, let's do some base testing on some preliminary work. And then let's do some higher end testing that's more expensive, just to see what our potential results could be. The challenge with all of this, and it's similar probably to a lot of research projects, the time and the money and the amount of blades that we were looking at. So our goal really was to just start doing some preliminary digging to see if things varied, if things were same. And then, recommendation down the line would be is to continue some of these tests on your own, whether it's within your existing labs or with a lab out there, to kind of see as these properties and these blades change, does that actually lead to higher blade wear, faster blade wear, or slower blade wear? So the first thing that we did here's two examples. The one on the left is from North Dakota. The one on the right is from Iowa. And we'll look at this here in a little bit more detail. And these were basically saying that the BSE, or the backscattered electrons here, which is part of the microscopy of this, just basically provides information regarding to the relative atomic weight of the regions being examined. So you see, you've got a carbide portion, the light color, you've got the brazed portion, and then you've got the blade portion, which again, I'm backing up here, which is consistent with the picture here you see in 417. So it's looking at the various spots in there, and we're trying to see, are there similarities between them, and are they different? And basically, in the BSC views there, regions appearing darker are atomically lighter relative to the atomically heavier regions. So what this does is it allows us to break down similarities and differences within those tests. The second set of tests that we looked at were both etched and unedged. So etched on the left, unedged on the right. And you can see here the pictures here of what that would look like. So this is a cross section using the blue dashed lines that we saw in figure of 419. So again, those blue dashed lines were on the bottom to the left of that blade. And so what they did is they looked at different structures. So now on the X side there, for the carbide component there, you see that the grains visually, they're different. And at this point of the study, or where we're leaving it up, we're not able to truly make a comment on which grain structure is better. What we are saying is that they are different for the same blade. One was sent to North Dakota, one was sent to Iowa, and you can see that the grain structures there, again, are slightly different. Now, on the unetched side, which is on the right-hand side of this figure, again, you see a North Dakota new blade, you see a Iowa new blade, and in this case here, the structures between the two are similar, which would suggest that the composition of the area that was tested is also similar. Again, it's just saying in both cases, what are similar, what are different, can we evaluate them? And the answer is in the final report, there are some tables there in 4.6 that break down based on all of the testing, the exact properties of the blades that are there. The other thing that we did is we looked at some polymer work here. And the polymer work specifically focused on the rubber. So you have the FTIR on the left, and then you've got which is again, which is a way of looking at it. And then basically what you do is you take the lines there and you look at a series of libraries that are already present and then are published. And then you can compare what those lines say versus what's going through. So the way it basically works is you've got a continuous beam of an electromagnet radiation is passed through or reflected off the surface of the sample. So in this case here would be the rubber. And what that does is it causes the individual molecular bonds and groups of bonds to vibrate at a characteristic. And then they're able to absorb the radiation frequencies. And so what that's saying is those different spikes there are different frequencies of how things are set up. And so from there, that line, we can then look at the library and see what is the chemical composition of that polymer spot. And then on the other side there, the TGA is a thermal analysis technique that measures the amount and rate of change in the weight of a material is a function of temperature. So what that's doing is it evaluates the various tests that we do. And then from there, what that allows us to do is then compare. So we generated, in this case here, we generated these figures for all of our different blades. And then from there, you're able to compare similarities and differences. And then the long-term goal would be okay, is it the differences? And then if there are differences there, some examples were silver versus nickel in the results. Does that then impact the wear? Is it that difference is the reason for the wear, or is it something else potentially that could be the reasons for the different performances in the wear? So we did a bunch of different different results, and what we did is we took the more comprehensive tables that we presented in our report, again in section 4.6 of the report, and we just kind of came out with some summaries. So some similarities. So the new North Dakota and used blade ring and carbide components were similar to one another. So they were saying that the new and used North Dakota ones were the same. Again, probably makes sense. Probably ordered them at the exact same time. Probably were delivered at the exact same time. So that makes sense. In terms of density of the carbide components, all of them were similar. And that's good. I was interested in that because my layperson thought on that is that the carbon may be changed in and out because it's a relatively expensive something. But it was nice to see in this case that I was wrong in my initial thoughts. Then we did some hardness testing there for the carbide components, and we saw that those two were consistent with how they were done. So some of the similarities, so this is good. So we are able to do some testing. We are able to show some similarities. So what that would suggest is that the manufacturing process is consistent in many cases. So that's a good thing. We did also find a couple that were different in those microstructures. So we saw in this case here, the North Dakota and the Iowa blade ring components different with respect to their chemical compositions and the resultant microstructures. And we saw that in the first set of figures that when you just visually looked at them, they were different. And again, what's important to mention in this project is differences do not necessarily mean one is better than the other. What would be interesting is that down the line, looking at those differences and seeing if there is whether you're in the field then, is there does the one perform better than the other? Those are some suggestions that we could do. Then when we looked at the blazing of the material used, we saw that the North Dakota New and the Iowa were different from one another in there, and that we saw when you boiled it down, and again, the brazing data is in the report, the big difference is one had silver and the other one had nickel. Again, not necessarily saying one is better than the other. We're just saying that they are, in this case, different. And so if one of them in the field was really great and the other one performed not so well, maybe, and this is, again, a big maybe a reason for it is the difference. Rankings, we also looked at that too, and we were able to look at them in terms of tensile strength, which we saw that the highest tensile strength was the brand new North Dakota. The lowest tensile strength was the North Dakota used. Probably not a surprise there too much. Again, wear and tear over the duration would maybe change it. Tear strength, we looked at it there. We saw that the North Dakota new and used were consistent with the other one, whereas the Iowa blade had a higher tear strength. And then the other one that we looked at down at the bottom was compression testing there. And we saw that they were, the North Dakota new and the Iowa were both stiffer than the North Dakota used as well. Again, so just some examples there. Now, what we tried to do is I just kind of used this as a page break to then say, great, you did a bunch of tests. Now what do we do? And so what we basically did is we broke this up to the polymer side and the metal side, and we broke it down into a few cost regions, which you can see here, which goes back to one of our earlier slides, which we were talking about low, medium, and high cost. And basically what we're seeing here, and this first one is the polymer, we've got that set up for some suggestions on what to do. And so like that FTIR process is about, in their case, they're about $1,000 to test two blades. And so what that's allowing you to do is that test alone, if you've only got a little bit of money, that test's going to allow you to do some different properties and performances and just kind of see what may or may not be more challenging. Then the next test would be to add the DFC and CGA tests there. And again, that's now looking at different compositions there in addition to, so each of these steps are adding on to what you would do before. So $1,000 would be one. The $2,000, you'd add the DFC and the TGA test. For $3,500 more, you would add the tensile, the tear, and compression. And these are just additives, right? So it's $3,500 total. And then that also becomes, those are just some suggested prices from one lab. It depends quite a bit on, how many more you're going to do. Are you setting up and doing a lot of tests, or, because that setup is cost, it can be expensive. Are you certifying those results, or are you just looking at them? So those are, again, a couple of different ways that you could look at. And then you can see down at the bottom all the tests that you could do. So it's got some different examples. There's to the left is this type of test. The middle column there is basically a basis for why you would do it. And then the last column there to the right would be some examples of why you would expect to see some of this data within the report. Here is the examples on the metal side there. So again, you've got a few price categories there as well that help you out. So each step down, so the OES, the blades, and the Rockwell hardness, and then the second one there would be, $3,200 ish. Would do those examples there, and what you'd expect to see, 5,000. and then going down some more. And then you'll see a couple spots there with some notes. Again, and that's really dealing with like the certifications, how much effect are you looking at on that. So those are some other ones that you would look at. So again, as you read through this in the final report, what we were trying to do is say, left column, this is what we would suggest. Middle column, this is why we would suggest. And then right column there, which ones there, what would be the expectations on how they would, or what they would do. So that's sort of an important one going forward. Then to sort of wrap everything up, what we were looking at here is looking at what would be the future work with the testing. So on one side you have field, the other side you have lab, and then how could we build this in a better way or in a different way? And so we were looking at this as sort of a flow chart coming down at the 20,000 foot view. You could do at the bottom to the left, you have formal testing, and you can do that both in terms of large scale and small scale field tests. And we have some standard protocols that we developed and are presented in the final report. And from there too, you could look at the cost neutrality of the blades themselves. The informal, we do that also all the time. Just look at a blade. Is it breaking? Is it not wearing? I mean, we've all been at a garage and you look at a blade and you go, that blade is garbage. And then what I would do is whether you're doing a formal approach or an informal approach, then take those blades of interest and then look at both what we said in the polymer and metal side, and then look at what your individual budget is, and then test a good performing blade and test a bad performing blade by those tests. And then from those tests, you could start honing in potentially on what were the differences. And maybe it's those differences for why a blade was wearing better or a blade was wearing worse in the field. And then while I don't have a slide on this, one thing that may be of discussion down the road is maybe there's a way through Clear Roads or another entity where states could post their own results and then again build up a repository of different results and then help with a solution. So with that, that's sort of a high level commentary or discussion today on our blades. So again, I'd like to thank you all for your time. Greg, maybe you can help jump back in at this point and we can go through some questions or comments, that kind of stuff.
All right. Thank you, Bill.
Thank you.
All right. Well, I don't see any questions in the chat box right now, so I just invite anybody who may have one. You can go ahead and take yourselves off mute and ask them that way, or you can put them in the chat box.
So this is Dave from New Hampshire. I actually have a question. I actually have some funding to actually take this project in particular and bring it to the field testing portion of it. And that was the premises of getting this money through our materials and research section of New Hampshire DOT. My question is, if I'm looking at these blades and I'm going to do some lab testing, my thought was to get an extra section, like a 3-foot section of the order, to send it to the lab as a brand new blade. Would you recommend doing the testing on a new blade or do the testing on the blade after it's been used, or both?
So this picture, so we did exactly that with North Dakota with their new and used blades, exact same blade, but some differences. If we had another 3 years of funding and plenty of time, what I would do is I would look at a new blade as a baseline. This is what we got this year. I would look at 2 used blades. I would try to find a used blade that you felt was good and wore at a rate that you deemed was reasonable, and I would look at a used blade that fell apart. And then I would go back through my numbers, what your budget is. And again, we give you some high level spots in the back that has numbers in there. And then I would, based on that, which tests I would run. And the hope that, and I don't know this would actually happen, but my hope would be that the assumption is that the drivers were doing proper techniques, and so the difference in the wear would be based on either a difference in the material or the process of which that blade was developed.
Okay.
Does that answer your question, Dave?
Yeah, I just didn't know where to test, if it was before or after, but you're saying kind of test both ends of it.
Well, so if you test before, what you get from the before test is a few things. You get are these blades consistent time and time again? So I kind of call that like concrete testing, right? Like you test every third truck and for a slump and all that stuff. So if you test them brand new, you get the base numbers. Now, I'm okay with testing new and then seeing how that base number changed over time, right? So if you test 5 blades right off the bat and you track those 5 blades through the winter, and well, no, you can't do that, because once you you've destroyed that blade or you've altered that blade. So yeah, I would test, if it was me, I would test after the fact a good blade and after the fact a bad blade. Those would be my first 2. And then if I had additional money, it would be interesting to see if you've got, let's say, 5 years of blades or 3 years of blades that were new and maybe never used. Was there a difference in those 3 blades? So you can at least see if it was consistent from the manufacturer. And maybe that's a good thing, and maybe that's not. I'm not necessarily saying that different consistencies leads to a better or worse blade. But I would definitely do it. I would definitely do it after the fact, good blade and bad blade.
Okay, I appreciate it.
All right.
And
Thanks,
Dave, if you want, I would be more than happy to set you up with the group that did our testing, and maybe they would provide some additional information for you. Dustin and Elena were very nice to work with.
Yeah, that'd be great.
And as a reminder, in addition to this recording being posted on the project page, this slide deck will be on the members only page at the top under research project documents. So for all completed projects, the webinar slides are up there. So you can get this contact information if you don't get it right now. Right. Anybody else have questions?
Yeah, this is Laura. I had just a follow-up. So just to clarify, for that research, you'd be better off to have like maybe an NS3, like look at 3 non-used blades and then 1 good, 1 bad, and then to see if the variability changes in manufacturing, and then you could see what those blades may go back and better compare with, good or bad. So instead of doing 1 and 2, are you saying then it would be better to maybe do a 3 and 2?
I think that's entirely on your budget on that side of things. What I would do first is I would do I would do 2 used blades, 1 good, 1 bad. And then if you've got, maybe do a couple samples there. And then if you've got the new, you can see how that comparison would be. Or in a perfect world, what I'd love to see is that, the state of Michigan and the state of Minnesota and the state of Ohio have collected a few their own, and then that data is compared to each of you, right? So then you can see, at the new level, are the blades different between Ohio, Michigan, and Minnesota? And then at the used level, are you seeing that your bad blade and Ohio's bad blade have the same composition? That's, in a perfect world, that's what how a state can do a little bit of testing and then do a bunch of little testing equal to one big test. I don't know if I answered your question, and I apologize on that if I didn't.
Nope, that works. Thank you.
All right, thanks, Laura. So Cliff has got his hand raised. Cliff, you there? All right, well, while Cliff is figuring out any technical issues he may have, does anybody else have a question?
Greg, this is Craig. I don't really have a question. I just want to offer up my sincere thanks to Bill from the project team for your work in this project. I know this has been a slog. I know we've had a lot of bumps along the way, but I think we finally got to the end here, and we have a good review and a good data set for us to really sit down and digest and go forward with. This has been a been a challenge, I know, Bill, but I just want to say thank you from the team for all your work.
I very much appreciate it. I want to thank you guys as well. It seems like we had a lot of no-cost extensions in there, and I appreciate everyone's patience along the way.
So Cliff did type into the text box. He said this was on high performance blades, but it looks like you tested carbide blades.
So ultimately, at the end, with the panel, we looked. The lab testing was on the Yoma blade because that was the most commonly used blade that we saw, and it had the most components to it as we were doing the lab testing.
Yeah, that was definitely the most available. That was part of the, after not being able to acquire blades, a number of high performance blades. First of all, we had to ask states what blades were they using. And when we didn't get enough of the cross section of different high performance blades that we were looking for, we kind of had to shift gears a little bit. That was one of the several times during this research project where we had to shift gears a little bit. And so we ended up, the project subcommittee decided to end up going with those Yoma blades. But the hope is that, when you test these blades, doing the field and lab testing that we did for this project, you would ultimately be able to apply those test methods to, high performance blades in the future. Because this, again, one of the main objectives of this project from the very beginning, from the time we first discussed this project at one of our spring meetings, was to, at the 18th spring meeting, was to identify a set of tests, a testing protocol that could be used for high performance blades, or any blades really for that matter, that come out in the future. And so it's not just about testing the blades, a certain set of blades that we currently have, but having a testing protocol for blades that come out on the market in the future and be able to test and evaluate those. So hopefully this project at least took a pretty significant step in that direction, if that makes sense. All right. Any other questions? All right, hearing and seeing none, I just want to let you know that, again, the final report is on the members only page for right now. As we finalize it, once we do finalize it, it and the brief will go onto the main project page along with this webinar. The slide deck will remain on the members only page under research project documents. And there is it was referred to in this webinar, oh gosh, I'm blanking on the name of it, it's due today. The comments are due today on it. hold on one second, I'm looking it up. Quick reference guide. The quick reference guide will be another deliverable that we'll put on the main project page, because I think that'll be a good source or reference information to be able for folks that are, anyone looking to learn more about this project. That'll be a good one. So the comments again are due today on that quick reference guide. All right. So I think that's it. Thank you, everybody. Thank you, Bill, for your presentation today and for all your work on this project. And I'll keep in touch with you on finalizing the last couple things. And thank you to the project subcommittee for all your work on this and staying with it, providing direction. And thank you, everybody else, for your support and for joining us today. Have a great day.
Thank you all.